Hello everyone, I'm Jernej Hribar and I'll present to you our paper, Analyze or Transmit, Utilizing Correlation at the Edge with Deep Reinforcement Learning. Providing energy necessary to power edge devices is becoming increasingly more challenging. For example, while connecting devices to the power grid is the most reliable way of providing energy, it also results in high deployment costs. At the same time, there's push for the entire IT industry to become greener. One of the ways to build a greener solution is deploying edge devices powered only by energy harvesting. However, in such devices, the available energy is limited. At the same time, especially in the last few years, we have witnessed unprecedented progress in machine learning methods that pave the way for many new analytic services that can run on these edge devices. In such scenario, as considered in our work, edge devices collect and process data to extract information of interest. And this all means that these edge devices are confronted with a decision to analyze collected data locally and transmit only the extracted information of interest, or transmit obtained data to a fusion center for processing. Additionally, our work also looks into the impact of correlation. In large deployments, the information obtained from individual devices is often correlated. For example, if we have a system of multiple cameras observing the same intersection, a lot of these cameras can detect the same objects in the intersection. And we really investigate how the correlation in the outcome of the data analytic task, what is the impact of correlation, the outcome of data analytic task to the energy efficiency of these edge devices. And we really ask ourselves, what are the possible gains that we can achieve for the system? And if we can use these gains to design a sustainable system, meaning that the device does not require any energy from the outside the device, meaning that all the energy it can collect is sufficient for the device to perform as the system wants it. So we can list our contributions as follows. We propose and formulate the problem of joint energy and accuracy optimization in energy harvesting edge networks with correlated sources of information. We propose a novel deep reinforcement learning-based algorithm that guides the decision for energy harvesting powered sensor based on available energy, task accuracy, and correlation. We evaluate the performance of the two variants of the deep reinforcement learning-based solutions with and without using Gaussian processes for energy estimation by using two established data sets to simulate the environment as accurately as possible. And we also compare our solution to 3 baseline policies. So we consider a system of K cameras transmitting information to the cloudlet server. The cameras can perform the task object detection by themselves or offload raw image to be processed on other elements available in the network, for example, cloudlet server. If the camera decides to process the image by itself, it can do so by using dedicated hardware that's capable of very energy efficiently process the image. For example, Edge TPU, NVIDIA Xavier, or Node Tensor can be used to ensure that the energy cost of processing on the edge device is lower than the energy cost of transmitting the raw captured image. Of course, the trade-off here is that the accuracy of detecting objects on the camera is lower than actually performing the object detection in the cloudlet server. And additionally, the camera can also decide to do nothing, meaning that it enters a standby mode in which energy consumption is negligible. In terms of energy, camera collects harvested energy in a battery of finite size. In each time step t, the camera consumes operational energy, E operational, and it uses this energy to capture the image and also to support any internal functions that the embedded device has to function. And then, of course, the other part of energy consumption is dependent on the action that the embedded camera takes. If it decides to detect objects, it will use energy that's required to perform object detection, and then, of course, to transmit the abstracted information to the cloudlet server. And if device decides to transmit the raw image, it will be the resulting energy cost to transmit will be much higher than if it just transmits information that the camera obtains by performing the data analytic cost. Of course, the main component of our system is to measure how accurate our object detection is, and for that we use recall. But first, we have to define set C as the set of all objects that are in the intersection. This set C represents the ground truth of the system that's only available, that's not really available in the real system, but in our data analysis, we have it. While the CK is the set of all objects that the cameras can detect. Due to numerous practical reasons, camera cannot really detect all the objects are there, because sometimes objects are just hidden behind other. For example, we have a car hidden behind the van because the vantage point of the camera is, because of the way the camera is positioned. And of course, to get the number of the object the camera detects, we need object detection. So if the image is processed on the cloudlet server, we assume that the system uses you only look once version 3 on the cloudlet server, or if we perform object detection on the camera, it uses tiny YOLO version 4. So each of these K that we have in our systems are different, even though they can be obtained the same time step. If we use YOLO, the number of objects will be different than if we use tiny. The reason for that is that with tiny, when we use on the device, we usually detect less objects. And of course, the total number of objects that the system detects is the union of the objects that all cameras detected. So this gives us a way to define recall, very simple. It's the number of all objects that we detected with the ground truth, which is set K divided by set C. So the length of both sets. And this also enables us to formulate the problems as follows. We want to maximize recall. Recall can be from this, can be maximum 1. And we want this to be for and we also want, and we are limited by the amount of available energy. And we also want that the camera experience downtime as minimum as possible for all time steps. So in our work, we use deep reinforcement learning to find a policy capable of maximizing recall and preserve camera's energy in a time-varying environment. We employ deep Q network algorithm, but also due to practical concerns, we use guard intervals. In real deployment, set C is unknown, but the system still needs to measure how good the object detection is. To that end, we use guard recall. At every decision step tau, all cameras transmit image. We then determine the guard recall by comparing the number of objects the system counted one step before the guard interval with the number of objects detected, at the guard at time tau. And of course, at time tau, because we have images from all cameras, and because we use processing on the cloudlet server, this gonna give us the best estimate of how many objects really are in the system. And this also gives us a very good comparison of how accurate our recall is, even without knowing the set C, because that is the ground truth, but the real system don't really have access to that. On top of that, we also use Gaussian processes to estimate the future energy the cameras will collect, which aid our solution in achieving no outages, as we show later in the results. So in terms of how we designed our solution, we were limited by the data set. So K that we consider is 2. We have 2 cameras in our system, and we designed our solution using 4 hidden layers. And as you can see, we have we have 6 inputs when we use the estimated energy. So we have recall, number of objects, the available energy of camera 1 and 2, and the estimated energy using Gaussian processes for camera 1 and 2. And of course, for output, we have 8 different actions, each representing, so both cameras, so we have 2 cameras, each one of them has 3 different modes of operation. So the amount of actions available in the system is 2 to the power of 3, which is 8. And of course, we have actually 2 solutions, one with Gaussian processes and one without. So in that case, these 2 inputs are not there, meaning that the system decides only based on these 4 inputs. And of course, our reward function depends on the recall value. And on top of the recall value, we also give high negative reward when the available energy in the system is lower than 10%. So our work is very much data driven. We use Cooper data set to estimate the accuracy. We use it to detect the number of objects, and we use another data set that reveals the amount of energy that our cameras can collect, and we use Gaussian processes. So if anyone is interested, here we have our GitHub notebook that shows how we use Gaussian processes in our work. So in terms of results, when we have, when the price and the price of transmitting the image increases, we can see that the greedy policy, which is the one when both cameras will always transmit, falls from 1 to 0.6, depending on the cost. So here is 1 because it means that the energy price of transmission is so low, the cameras can afford to always transmit, and this is usually the option. So as you can see, our proposed solution using Gaussian processes can come very close, but it still cannot get to 1. So this is due to exploring in our solution. And of course, we can see, but of course, as the energy price increases, all solutions become lower, and at certain price, the learning solutions start outperforming the other policies. You can also see in terms of the downtime that all greedy, all threshold policy that decides if it's more than 50% of energy available, the camera will transmit the image. If it's less, it will try to use update hash on itself. So you can see that both greedy and threshold policy result in a relatively high downtime, while both our relevant solution achieves relatively low ones. So alternating is just the one that will be alternate over all 8 options. And you can see that when you use Gaussian processes, when you give the system more information about the future energy, it outperforms. So in the next experiment, we just randomly changed the cost of transmitting at every decision type's tau, so at every tau, and you can see that the proposed solutions both outperform all others. At the same time, the solution that uses Gaussian processes results in very little downtime. So in conclusion, our results show that the proposed approach can be up to 50% more accurate with no outages. In our future work, we'll examine the scalability of our solution, and then we'll have more than 2 cameras in our system. And we will also add another dimension to our work by considering latency. Thank you very much for your attention and for listening to my presentation.